Chapter 8, and then do the last problem, Chapter 8, the synthesis one, sure. All right, dehydration. My pen here. All right, the mechanism for a dehydration is E1-like. And when I say like, we don't have an alkyl halide. Remember, the E1 reaction was you have a leaving group leave, and then you form a carbocation, and then it eliminates. Well, this is the same type of thing, but in this case, your leaving group is going to be water. That's your leaving group. So you'll take an alcohol. You'll add some sort of strong acid, either like sulfuric acid or something like that. Add heat to it, and you form a double bond. And you also form water as a byproduct, because that's your leaving group. So this oxygen with the hydrogen is going to be the leaving group. Let's make this green. So just to kind of show, kind of like doing this just so you can see, it helps with the mechanism to see where everything goes. Okay, so the first step is the oxygen, not lone pairs. Protonate. Form a water molecule as a plus charge. So this is going to leave to form your water molecule, which we just formed here, plus a carbocation. Oh, also, guys, I posted chapter 8 and 9 quiz. So if you guys get those done, I'll give you the answers. I'm not going to post them because I gave everyone until the end of the semester. So if people want to wait that long to do it, that's fine. But if you want the answers sooner, I'll give it to you. So then another water molecule, I have it written as 8OH2. It doesn't really matter how you draw it, but water comes by to pluck off that proton. This regenerates H3O+. You form that, and then this thing kind of spits out. You form another H3O+, which is our catalyst. So that's the regeneration of our catalyst. Actually, it gets regenerated by the hydrogen on the carbon. That's kind of how it regenerates. Okay. Ashley said, awesome, thank you. Yep. And then, let's see, chapter 8. Chapter 8, last problem. Oh, the last, you're talking about this one right here? I think that, Anna? That one? Yeah, okay. So, this is two pieces, so basically all of the carbon sources have to come from these two compounds. All right, so let's just copy and paste everything. And grab my handy dandy tool. I'll load. Okay, so we're making an ether. All right, so how do you make an ether? The way you make an ether is Williamson ether synthesis, so an SN2. So oxygen on one side and alkyl halide on the other. It doesn't really matter where your oxygen or alkyl halide is, but by looking at this, it looks like it'd be easier to have the alcohol on this carbon and have the alkyl halide on that carbon. Just because I already have an oxygen here, I know how to turn a carboxylic acid into an alcohol very easily, and I can turn this into an alkyl halide very easily. I could also make this the alkyl halide, but I have to add an additional step in the synthesis. So just by looking at that, it looks like this probably would be the easier route. You can do it either way, no matter how you did it. It's acceptable. And let's put a chlorine there. You can put whatever you want. So in order to make this compound from the starting material, you just add HCl. So that shows how to make this compound. And then this one, we're going to go back one. To make that O negative, you start with the alcohol and you add either like sodium metal or you can add like sodium hydride. We talked about that. Either one of those is fine. And then to make this alcohol from this carboxylic acid, you just have to reduce it with LAH. And the second step is adding acid to it. All right. Now, if you wanted to, you could do the opposite. So you could have turned this into the alkyl halide if you wanted to. Have this as the halide. So you would add SOCl2 or HCl, and then you would just take this and add acid and water to it to form the alcohol, and then add like sodium or sodium hydride to it to form the O-. So either way, you can either do it this way to get these two compounds, or you could do it this way, which is less steps, but either way would be correct. Okay, does that make sense? Who asked me that? Ashley asked me that, or Anna? I think Anna, yeah. Anna, you did, yeah, okay. Good. Was there anything in particular you had trouble with? Because why only the last one? Were you okay with all the other ones? Like, what about this one did you feel you were struggling with? If you want to go off the mic, that'd be easier, if you want to tell me. First
yeah, I okay on the first and third one, but
okay.
For some reason the last one I think was just it was tripping me up.
Okay. So do you want to go over the second one, or do you think you got that one?
We can if you don't mind, I'd like to go over it.
I don't mind. I mean, it's only the four of us, so
yeah, that'd be awesome then.
Okay. Yeah, we can go over that. So this one you use the cyclohexene and ethine. So obviously these two carbons are coming from ethine. All right. So again, you can do this with only chapter 4 reactions. You don't even have to do any chapter 8 reactions. So let me grab it. But on the exam, I will clearly say make sure you use chapter 8 reactions. So I'll show you both ways, without chapter 8, and then I'll show you with chapter 8. Because it depends on how you did it. So here we have a ketone. All right, we've learned several different ways of how to make a ketone. Just doing chapter 4 reactions, the way that you can do it is if you have a double bond here, add the mercury sulfate and acid. Remember, that goes to the enol, and then it forms the ketone. And then to make this, you have to take the ethine. So let's put this here. Take ethine, which is one of your starting materials, and add it to the cyclohexyl chloride. No, first you have to have NaNH2 to pluck off the hydrogen, and then you add the cyclohexyl chloride, which you can make from the alkene and HCl. So that would just be all chapter 4, right? Does all that look familiar to you guys? That's all the chapter 4 reactions. Okay, but to do a chapter 8 reaction, to try to include a chapter 8 reaction, we would have to make this an alcohol. So basically I would make this. So here's now going chapter 8 direction. All right, look at your chapter 8 stuff. What I would most likely do is I would do a Lindlar's catalyst right here. But obviously it would be more reactions. In reality, I'd probably just do the chapter 4 because you want to do the least amount of reactions as possible. And then I would add acid. Give me that. Oh, no, that's not right. add the acid to make the alcohol. And then I would oxidize it, either PCC, in this case PCC, PI, the CrO3 in acid, or the Na2, Cr2O7 in acid. I didn't have room really to write it. But. So that would be the chapter 8 route. All right. Does that make sense? So there's 2 routes. Most likely, I would have you, not most likely, I would have had you have tried to done the red route, because I would want you to get some chapter 8 reactions in there. What I probably would have done was actually had this as the product. So guys, think about what you would do in that case. So just to change the problem around, I made this a while ago, a long time ago, but now thinking about it, I'd probably change it to this as the problem, because this forces you to actually do a chapter 8 reaction. Okay? So I'll give you a hint. You still would make this. Okay? But now show me what I would do in order to get to there. I'll give you guys a little bit of time to think about what reactions you need. I'm going to put this on pause. All right, so in order to get the aldehyde, we know that you have to oxidize primary alcohol, PCC or PI. Choose whichever one you want. All right, to get the primary alcohol, especially since we know, well, we got to make this into a double bond. So Lindlar's. So remember, we're still going to be using reactions from other chapters. And then you got to do anti-Markovnikov. All right, so that would be how you would make the aldehyde. That's more like something I would probably have on the exam, because it forces you to actually use a reaction from chapter 8. Okay? Good. All right, so is there anything else from the book or the problem sheet that you guys want to go over? Those are all good types of questions. Again, if you want to go off mic and just say it, that's totally fine. That might be easier. I think there's an error in one of these assignments. Problem. I think it was page 8. Yeah, it was this one. In this one, that carbonyl should not be there. It should just be an alcohol. You actually know how to do this based off of chapter 10, but that carbonyl should not be there. Erase that carbonyl off of the homework. So if that was confusing, that was miswritten. I might have changed it in the answer guide. Let me see what I put in the answer guide. Yeah, you see in the answer guide, I erased it. Took it off. So ester, LAH, gives you the alcohol. Just making sure you guys notice that. All right. Okay. Anything else you guys want to ask about? This is the time to do it. I don't really have too much. I mean, I feel like we've gone over a lot of these problems in the book last week. I probably have 1 or 2 syntheses that we can work on. But mostly it was to answer any questions. All right, Andrea. Andrea, if you can go off the mic, it's a lot easier to do that.
Yeah, plus
okay.
it's a kind of a longer question.
Okay, good.
It's not specific. I didn't have a specific problem
okay.
or anything, but it was more over kind of like a Grignard rule. I remember yesterday we were talking about whenever you use a Grignard, you can't have like a double bonded oxygen OH because it'll react on itself.
Right. Right.
Is there any other limitations?
So So let's talk about that. But just so you know, the Grignard stuff is 9 and 10. It's not in Chapter 8. So I just want to make sure that you realize that. Yeah, but I'll go over that because it is still important. Okay, so Grignard, you've got to remember that a Grignard is a very strong base. It has a negative charge. It's a carbon that has a negative charge. Right? Carbon does not want to have a negative charge. So this thing will react with anything it can. All right? Any type of a partial plus charge, it doesn't matter what it's from. It doesn't matter what atom it's from. This thing will immediately react. All right? It's probably the strongest of all of the nucleophiles that we have. All right? So if I have a carbon negative, okay, anything partial positive it's going to react with. So if I have an acidic proton of some sort, so imagine I throw in here a carboxylic acid, all right, this Grignard is going to immediately grab that proton, right? It has a choice of either attacking the proton, or a carbon here is also a partial positive. So the hydrogen is partial positive and the carbonyl is a partial positive. But which one of these do you think is easier for the Grignard to actually grab onto? The answer is the hydrogen. The hydrogen is just hanging out here in the open, where this carbonyl has an oxygen. So remember that this is actually a trigonal planar, and I have a carbon here with a whole bunch of hydrogens plus an oxygen that has its lone pairs, that are hanging down, plus I have hydrogens here. So this carbonyl is hard to actually try to get to. So if I had a nucleophile of some sort, it has to squeeze in between all this, where this little hydrogen is just hanging out all in the open. So if a Grignard had a choice between this partial positive site or this partial positive site, it's going to choose a hydrogen immediately. All right. If I had a nitrogen on my compound and anything else, again, my hydrogens here are partial positive. So this Grignard immediately is going to grab a hydrogen before it does anything else. So any type of acidic proton, and when I mean acidic, I mean it has a partial positive charge to it. So alcohols have that. Carboxylic acids obviously have that. They are very acidic. Amines have that. If you have a thiol in here, it has that. What else have we learned about? That's pretty much all of the OH groups. So alcohols or acids, any type of acidic proton, anytime you have a hydrogen attached to a non-carbon atom, that Grignard is going to pluck that off first. And it's called quenching the Grignard. Like if I have a Grignard, a methyl Grignard, right, and I have an acidic proton here, it's going to immediately grab that hydrogen and it gets protonated and it turns into methane, which is a gas, and it bubbles away. I've quenched my Grignard. It's not really attacking what I want it to actually attack. Okay, so that's number one. You can't have any type of acid, even water. These reactions have to be done dry. How you actually do them is you actually flame dry all your glassware under vacuum. You take all the glassware and you close it off and you put it under vacuum, and you take a Bunsen burner and you actually flame dry all your glassware. So you make it really, really hot. So it evaporates all the water inside of your glassware, and it's under vacuum. So all that water vapor is all pulled out. And then once all of the glassware has cooled down, then you undo the vacuum and then you do the reaction, knowing that you don't have any bit of water in there. So everything has to be completely dry. Your reagents have to have been dried. It's hard for us to actually do a Grignard in our labs because it takes special equipment in order to dry all that stuff. I mean, it is possible, but Grignards are hard to actually do because of the fact that everything has to be really, really dry. Because if you try to actually make a Grignard, if you have any type of water or acidic proton, that thing immediately will grab it and it quenches it. Okay, so that's number one. Number two is Grignards, again, attack carbonyls. Okay, and it's not all picky which carbonyl attacks. There are some of them which it's more picky about, but pretty much any type of carbonyl, because what do I have on a carbonyl? I have a partial positive. Like I said, Grignards are looking for any kind of partial positive that it can find. Okay, and H plus is the most reactive, but then after that, any kind of carbonyl. Again, any partial positive, this thing is going towards a partial positive. Okay, so ketones, aldehydes, esters. Obviously not a carboxylic acid, because like I said, the first thing it's going to choose is the acidic proton. But if I don't have an acidic proton, then it's going to go for a carbonyl. So if I have a ketone, it will go for the ketone. If I have an aldehyde, it will go for the aldehyde. If I have an ester, it will go for the ester. If I had anhydrides, it will go for the carbonyl on an anhydride. All right, acid chloride will go for the carbonyl on an acid chloride. So any of these carbonyl compounds that we learn in chapter 10, that's what it's going to go for, as long as I don't have an acidic proton. Like I said, that acidic proton is number 1. That's the first thing it's going to go for. So you can't have any of these on there. So number 2 is a carbonyl, something that has a partial positive. Okay, well, let's say I have a Grignard. All right, let's just do a methyl Grignard. And let's say I have this compound. Let's say I have, let's put a ketone there, and let's put an aromatic ring here. Okay, let's call this carbonyl 1. Let's call this carbonyl 2. Okay, which carbonyl do you think this Grignard is going to prefer? All right, so write in the chat box 1, 2, or say no preference, like NP, or both. You can say both. B for both. So prefer 1, 2, or both. All right, so far half the class is answered. Almost all of them. Okay, well, actually, all of you are 50% correct. Both. Anna is the correct one. This does not have a preference. If there's a partial positive, it doesn't matter what the partial positive is, it's going to go for both of them. So steric hindrance, I think everyone's saying 1 because it's less sterically hindered. Actually, they're about equal. But steric hindrance has a slight effect to it. However, you would probably get a mixture of compounds. I would get either the product where it reacts to 1, or I would get where it reacts to 2. I might even get a bunch of compounds where it reacts to 1 and 2, and I form both of those alcohols. So the point is Grignards react so fast, they don't really have a preference. They will, whatever is positive, it will go for. Okay? So that's why usually when you react to Grignard, you have to only have one group on everything that has one partial positive group on it. Okay? So yesterday, I think it was Anna, right, Anna? Weren't you the one that had the ester on there? Yeah, it was Anna. I think you had the ester, right? So what she had was an ester. Oh, that's a weird-looking ester. That's a peroxide ester. She had an ester and then a Grignard on the end of the ester, trying to react it onto another carbonyl compound. Let's just assume it was that. Well, all based off of everything I said here, what's the problem here? The problem is I have a partial positive here, and I have a partial positive here. So the Grignard technically has a choice. It's not going to discriminate between this carbonyl or that carbonyl. It doesn't care. It's not like it has a brain. It's just going to find anything that has a partial positive. It will react with itself half the time. Yeah, in fact, they'll probably do it more of the time because this carbonyl is attached onto it. It's right there. This has to find this compound, right? Like imagine if you were in a club or a stadium or something. It's very crowded, and you were holding hands with one person, and you guys had to find another person. Obviously, the one that you're holding hands with, you already found them, right? They're right there. And then trying to find that other person is a lot harder to do. So as soon as you made this Grignard, it'll probably wrap around itself and react onto itself. So that's why you can't have other partial positive groups on a Grignard. Grignards are really hydrocarbons, and it could be any kind of a hydrocarbon. Like I can't make a Grignard that has a carboxylic acid group on it, right? What would the problem there be? So imagine I had this and I made a Grignard like that. right? Well, as soon as I made this Grignard, it immediately plucked off a hydrogen, an acidic proton, either on itself or it would find another carboxylic acid and pluck off the hydrogen. Okay. However, if you did want to make a compound like that, let me clear up some space here. You can actually do this if you wanted to. Control Delete. Like if you, let's say you had this compound, and you had a Br, and you added magnesium to it as your first step, and your second step is adding acid. Right? What would be the product of that? Well, I would make the Grignard, and then 1, 2, 3, 4, 5, 6. It would immediately cyclize onto itself and form that compound, which is actually a reaction. It's pretty cool. It's a way to make a ring that has groups on it. Okay, because as soon as you made the Grignard, you would have this MgBr. Which, remember, I have a carbon that has a minus charge, and it would wrap around itself and add onto there. And then those electrons would all pop up. So you'd have a 1, 2, 3, 4, 5, 6 membered ring. Okay. So, Andrea, was that you that asked the question? Yeah. Thank you. That was okay. Good. Yep. No problem. So, pretty much, again, you can't have anything partial positive, or if it has a carbonyl, it's going to go after carbonyl. It doesn't really discriminate. Now, in real life, yes, you can kind of make it react on things more than others. Like if you did have an ester versus if you had an aldehyde. Technically, this has been done, but under very special, you have to change the solvent, you have to do it in cooler temperatures. Put the lone pairs here. It would actually react on the aldehyde much faster. Now, this is just all going more into it. As far as we're concerned, just assume it's equal. Okay, but you can actually get this to actually react on the aldehyde over the ester. And why do you guys think that is? I'll let you guys think about it for a second. But why do you think the Grignard would prefer an aldehyde over an ester? And I'll give you a hint. Sterics don't have anything to do with it. It kind of does a little bit, but there's something else that's going on here. What do you guys think? You guys have any idea? Excuse me. The thing is, because of these lone pairs on this carbonyl, you kind of have this kind of a somewhat of a resonance structure. So what it does is it makes this carbon not as partial positive as our carbonyl. So this has a much smaller partial positive compared to here. We have a much larger partial positive. So all because of this resonance going back and forth, this carbon in the center does not have that much of a partial positive because it has these electrons that are kind of being all pumped into it. So it makes, and the carbon here does not have that. So in a case like this, the Grignard would attack the aldehyde more, but you get a mixture of the two. Okay, so hopefully that goes a little bit more into it. Okay, anything else you guys have? Is that good? All right, let's do a synthesis here. Trying to think which one I want to do. That's a good one. All right, we're gonna start with this. Start with benzene. All right, and synthesize. Now the problem with doing just chapter 8 stuff is a lot of people might want to use reactions from chapter 9 and chapter 10, which is totally fine. I am totally fine with that. If you're like, oh, I can do that easier with just chapter 9 reactions, I'm fine. But don't just do chapter 4. Try to incorporate, I think in this one you have to, I'm kind of forcing you to incorporate chapter 8, reactions. But you don't have to just do chapter 8. I mean, you can just do chapter 4 if you want, chapter whatever 5, and chapter 8. That's fine. But if you want to try to include 9 and 10, I'm fine with that as well. Okay? So I'll put this on pause, and then when you guys are ready, just put R in the chat box. All right, let's go over this. So I got a carboxylic acid. All right, so that implies that I need to get an alcohol at that position right there. All right, so I need to get an OH right here so that I can oxidize it, CO3, an acid. I can't just attach a carboxylic acid onto an aromatic ring. All right, I can't do that. All right, the only way to attach carbons is the Friedel-Crafts alkylation or the Friedel-Crafts acylation. And in this case, we're going to do the acylation. So remember, you take the acid chloride and AlCl3 as a catalyst to put on that group. Okay, so if you remember from chapter 5, you either can add a hydrocarbon. This is either carbons and hydrogens. You can't have a double bond or anything else attached to this. This all has to be single bonds. All right, so if some of you if you had like a double bond in a chlorine there, that would not work. All right, it's got to be either an acid chloride or a hydrocarbon, or an alkyl halide. So I'm not sure. So I know a lot of people sometimes try to do this. They take a carboxylic acid and then they put like something like that, try to attach that onto there. That does not work. Okay. You have to remember from, was this chapter 5, this was either a hydrocarbon with a chlorine on it, or you can add an acid chloride. All right, and then what I would do is reduce this, so sodium borohydride and acid, 1 and 2, to get the alcohol, and then I have to eliminate it. Double bond, and then do anti-Markovnikov. To get the primary alcohol, and then oxidize it with CrO3. All right. That's really, I think I can see the only way to do it. If you did the Friedel-Crafts alkylation, you just put an ethyl group on there, and the ethyl group has no handle on there. You can't really do anything. You could have done a Grignard. What you could have done was you could have turned this into a bromine. Again, this is a chapter 9, but if you did it, I was fine with that because you'd also use reactions from chapter 8 too. You turn into a bromine, and then eventually into a Grignard, and then you can add it to this aldehyde, and that would basically make this alcohol right there. So that would be another way to do it. Okay. Anybody have any questions on that? Or do you have something that you did and you want me to check? Because there might be another way that I haven't thought about that maybe one of you've done. But like I said, the most common errors I see is this thing, like I was saying. When you do the Friedel-Crafts, people try to add on everything that they want to do. I'm just letting you know, none of these synthesis is going to be 1 step or 2 step. So if you think, oh, I'll just attach the whole group on, you should think to yourself, yeah, that's probably not the way he wants me to do it. Well, that's probably not the way that it will work. If I have a carboxylic acid or an aldehyde or something, I'm going to want you like to show me an oxidation, right? Because these, I'm trying to force you to use reactions that are new in this chapter. So always keep that in the back of your mind when you see a synthesis. Don't just think, oh, I'll just attach the whole entire group, because that's, not the way to do it. Okay, so it's kind of like a strategy hint, I guess, on exams. Okay, so don't. Let's see what Kelly said. I'm sure it's gonna be funny. Don't say yes, exactly, exactly. Know that I'm trying to test you on your knowledge of the reactions. I'm not trying to get you just to do a one-stop shop type of thing. It's something I'm trying to get you to think about. And this was about 6 steps. Is probably like 5 to 6 steps. Is probably the average type of steps I'll probably try to have you do on the exam. And since this is just on one chapter, I'll probably just have one synthesis problem, because then I'll have one for chapter 9 and then one for chapter 10, like stuff like that. So I'll probably just have one synthesis problem. I'm guessing this will be like a page and a half to 2 pages of an exam. These exams are usually, 8 pages, something like that. So maybe it might be 3 or 2.5 pages, something like that. I'm just going to take, an exam, and basically I'll find all the stuff I did for chapter 8 on that exam. That's kind of what it'll be. All right. So you guys have any other questions or concerns? I'm going to keep this open probably for the next hour, just in case people do come in and have questions. But otherwise, can we do a problem like number 2 on the quiz, going from a dehydration reaction to then reacting with sodium metal? Which quiz are we talking about? Like the quiz for chapter 8?
For chapter 8.
Yeah, we actually did that at the beginning of class. For today, there was that synthesis problem that Anna asked me, and we actually did that already. That's just in SN2. It's the Williamson ether synthesis.
Gotcha. Okay.
So yeah, so it was like that problem. Let's see if I can pull it up again. It was the synthesis problem. That's not it. Where was it? I'll just remind you where it was. It was like that one right there. Right? If you remember, we turned this into an alcohol, and then I added the sodium metal to it, and turned it into a negative charge, and then I added it like to this alkyl halide. I had to turn that into an alkyl halide. Does that sound familiar? Okay.